Hi there. Thanks for joining us on the Space Nuts podcast. My name is Andrew Dunkley, your host, and it is great to have your company yet again for this episode 319. And coming up in this program, we are asking the question, could there have been more than one dinosaur asteroid? We know about the one that created the Chicxulub crater, but they're starting to size things up and there might have been something else. We're also going to talk about something that astronomers took a photo of. It's the sharpest image ever of the R136A1 star. So what's so good about that? It's just the biggest star in the universe, or second biggest if you don't count Fred. And questions about Dyson spheres, the Barry Center, and cosmic microwave background radiation, all to come on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Just snuck in a little tickle while that introduction was on. And joining me as always is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. It's not just the astronauts that are reporting it feels good, it's the host of Space Nuts as well.
Yes, just a little, because it's the end of the day here. So, you know, if you're watching this at 5 o'clock in the morning and thinking, ew, why is he drinking wine? No, I'm not. It's getting on towards 5 p.m. our local time here. Fred, good to see you. How you been?
Well, thank you. It's the end of the day here too, by coincidence, but I haven't got a glass of wine, I'm afraid.
I'm sure someone will turn up with someone sooner or
you never know.
With one soon.
Something might happen.
Yes,
right.
Indeed. Well, I hope you're staying well and staying dry.
Yep, we got some rain last night, but I don't think we got anything like as much as you did. We had 12 millimetres in the gauge this morning, which is not that much.
We've had rain every week for the last, I don't know how long. Our dam is back to bursting and they keep emptying water out of it to keep the air in it for flood mitigation, but it keeps filling back up again. And it's hard to really believe that 2.5 years ago it was down to 6% of capacity at the end of that massive drought. And now it hasn't been below 100% for 2 years. Extraordinary.
Barrendong Dam, is that right?
That's Barrendong, yeah. It's well, when it's at 100%, it's 3 times bigger than Sydney Harbour, but when it hits flood mitigation level, it gets up to about 5 times bigger than Sydney Harbour.
Yeah.
It is a big, big piece of water. But I'm sure you can see it from space, to be honest.
Oh, you would, yeah. No, it's an enchanting place as well. It's
lovely.
Delightful place.
Nice area too, yeah. Now, Fred, let's get down to business and talk about these stories that have come up in astronomy and space science news this week. Could there have been more than one dinosaur asteroid? I found this story fascinating.
Well, we're all totally fascinated by anything to do with the event that wiped out the dinosaurs, aren't we? And this just compounds the mystery, really. So there is a crater which has been identified actually in the Atlantic Ocean off the coast of Africa, and it's sort of on the edge of the continental shelf of Africa. So it's in water that's not, humongously deep, but it is pretty deep. And it's been the really interesting thing, and this is what makes me admire these the geologists who do this work so much, is that it actually isn't visible on the seabed. It's buried beneath sediment underneath the seabed. And so you have to infer its presence by, fairly complicated means. And one of the ways that they do it is by seismic measurements, so that you can actually map sort of what's under the sediment by looking at the way seismic waves travel through the Earth's crust and through the mantle.
Yeah.
And so the scientists who've done this have actually mapped it. It has a name, which is nadir or nadir. That to me means the point that in the sky directly looking downwards. The zenith is directly over your head. The nadir or the nadir is beneath your feet. But it takes its name from seamount, a mountain that is actually on the ocean floor off the continental shelf, which is called the Nadia Seamount or the Nadia Seamount.
Right.
And so this crater, which has now been identified, not very far away, it's probably 100 kilometers away, which on a global scale is not that far, has been recognized as having characteristics which have been mapped pretty accurately by the look of things, that suggest, first of all, that it was an object, it was a crater formed by an object something like 400 meters in diameter. And at the time this impact took place, the ocean was about 800 meters deep. So it went straight through this ocean column of water and hit the surface and basically created a crater, which is now underneath the sediment down at the bottom of the ocean. But what's happened is that the scientists who have looked at this, they've kind of looked at not just the impact itself, but looked for surrounding debris and things of that sort, which are still there. There's still evidence of the fallout from this huge explosion that would have taken place when this asteroid hit. And it's because of all these studies that the scientists have been able to date the Nadia crater. And what they have come up with is the really interesting insight that it's roughly, give or take, maybe a million years perhaps, it's roughly the same as the Chicxulub crater, the impact that, the crater formed by the impact that wiped out the dinosaurs at the boundary between the Cretaceous and the Paleogene periods, 66 million years ago. So it's roughly that same age. And so, that immediately raises the question, well, is there a relation here? And we do know that asteroids do break up. And as do comets. In fact, we saw one actually happening back in the mid-90s, 1994, when Shoemaker-Levy 9, a comet, which was actually closely approaching Jupiter, and it broke up. The gravitational tidal effect of Jupiter broke it up. So you got several fragments colliding with Jupiter over several days. And the suggestion is that perhaps that is what happened with the Nadia crater. It was a bit of a chunk of the same asteroid, maybe formed by tidal effects as the asteroid got near the Earth, or maybe formed by an earlier collision while it was still on its way. If it collided with something else, and then suddenly you've got a pile of debris all going in the same direction at the same speed. Okay. So you might get multiple impacts.
So they're saying these two hit around the same time. Is that what they're suggesting?
Yes, that's right. That's the suggestion, because it's got the same age. Now, by the same time, they don't necessarily mean the same day. Right. It could be, the same time within 100,000 years. Because they don't know that yet. But that's the best bet at the moment. And so what these scientists want to do, and that's the next step, is to do what scientists did a few years ago that we talked about a lot, Andrew, get a drilling rig and go and drill down into the below the sediment and look at the structure of the rocks underneath where the impact crater is. That's what happened at Chicxulub. Yep. You remember the drilling vessel had a funny name. Was it Mabel? I think it was Myrtle. Was it Myrtle? I can't remember.
I think you're right. Like I was going to go with Boaty McBoatface, but yeah. Myrtle sounds right.
The step up, I can't remember. Anyway, that actually proved that this was that it was an asteroid impact, because they found shocked quartz and stuff like that underneath the surface of the sediment, and so that's what the scientists who are working on this project want to do next. And by the way, they're from a university not far from where I was educated. It's not the same one, Heriot-Watt University, which is in Scotland, and also the University of Texas at Austin. And there is also a scientist from the University of Arizona. So it's a fairly strong team there, and they are dead keen to go and find out whether this really was the same asteroid that wiped out the dinosaurs. And I guess what you do to prove that is to look at the isotopic composition of some of the rocks and find out if you can do a match from these, this kind of chemical fingerprint or this atomic fingerprint that you get from that.
Odds would have to suggest it was. It would be a huge coincidence to have two independent asteroids hitting so close together, but, maybe not.
Yeah, the reasoning on that is quite interesting. So for a Chicxulub-sized asteroid, which is 15 kilometers or so, that's a huge piece of rock. You expect one of those every 100 million years or so. But for a 400-meter chunk of rock, you might expect one every 700, 800,000 years. So it is possible that it could have been completely unrelated. If you've got rocks, if you've got that sort of interval between impacts that size. Of course, an impact that size would still have pretty devastating consequences on the local environment.
I imagine so. I also wonder, though, if the second one, which one hit first? Chicxulub?
Who knows?
Oh, right. Okay.
We don't know the answer to that. What they do say, actually, it's a conversation article that's not that hard to find, Andrew. They also say that the impact would have released energy. This is the Nadia crater, would have released approximately 1,000 times more energy than what we had from the Tonga eruption recently.
Yeah.
And that was pretty good because that sent pressure waves all the way around the Earth and tsunami waves. This would have been 1,000 times worse than that.
And I read an article about some of the amazing sunrises and sunsets we've been having recently.
Yeah.
And that's all because of the Tonga eruption. Because of all the dust that's in the air.
Yeah. My colleagues of mine at the observatory are recording those, and they're noting, it's really quite pink skies.
I've taken some amazing early morning photos because, I get up at Sparrows because I have to do the radio show at breakfast. But Sparrows is an Australian way of saying, because when sparrows wake up, they go, sparrows, whatever.
It's an abbreviation, yeah.
Just look it up. I'm not going to say it. But
we had it in Britain too.
Yeah. I'm just wondering, though, had one or the other not happened, would the dinosaurs have survived?
I think they would have survived the Nadia crater impact, because it's a much smaller event. So its consequences would have been, the size of a continent, but not global, whereas the Chicxulub one definitely had global consequences.
Yeah. So anything swimming in that vicinity at the time probably.
Yeah, that's right. Yeah.
Probably didn't have a very good time.
It will be curtains for that.
Yeah. It's just hard to fathom, the devastation, the size of the areas that could be devastated by these kinds of events, like 400-meter asteroid. Yeah, there's a continent.
Yes, that's right.
And we've talked about it before, depending on the size and impact point and certain other factors, how big the devastation is. We've talked about asteroids that could cause statewide devastation, regional devastation. And it's not always size. I think we did a story once about the factors that do come into play.
Yes, we did.
Size is not the absolute factor, which makes it's even scarier when you think about that.
Yes, it is. It's not just the big ones.
No,
it's the others as
well.
well.
The small ones, if they hit the right way, can be super devastating.
Yeah, hitting the right kind of terrain. I think, if I remember rightly, that thing we covered was that if you hit it in the water, you get more of a devastating effect. And maybe that's what happened with the Nadia crater.
Yeah, maybe.
Splashed in the water. So maybe it did contribute to the death of the dinosaurs. We can but speculate.
We can, but hopefully one day not far away, they will send an expedition out and do a little bit of a drill and see if they can come up with an answer as to whether or not it was a totally separate and independent asteroid impact or was related to the Chicxulub asteroid.
Yeah, if it can show it's two bits of the same asteroid, that's pretty convincing. Yeah.
Very interesting. All right. Hopefully more to come on that story in the not too distant future. This is Space Nuts. You're with Andrew Dunkley and Professor Fred Watson. Let's take a break from the program to tell you about our sponsor, NordVPN. Now, I've talked to you many times about a virtual private network and the advantages of having one. And it is true. A lot of people don't need convincing, but it also comes down to the quality of service, and you'll get no better than NordVPN. They are the leading service. They can block trackers. They can check downloaded files for malware. They can just make sure that your whole system is not being infiltrated, whether that's by hackers or by opening an attachment to an email that you probably shouldn't have. And they're highly backed. A lot of big organizations believe in this product, and so do we. Now, if you're a Space Nuts listener, you get a special deal, which I'm going to tell you about in a moment. But, there are all sorts of situations where you're exposed to problems online, such as hackers and viruses, whether it be at home through your email service or through using public Wi-Fi. All of these things can put you in danger. And with NordVPN, you can protect up to 6 devices at once, from your smart TV to your smartphone to your computer, you name it. And it's as simple as just joining NordVPN and downloading the software. But at the moment, there is a special deal for Space Nuts listeners. Now, all you have to do is go to the special URL that's been set up, nordvpn.com/spacenuts. There's an exclusive deal, the NordVPN Cyber Security Package, all inclusive, plus 4 months free. That is a fabulous deal and pretty simple. Other advantages, of course, you access the global internet, you get shielded from cyber criminals, and you can secure all those devices I was talking about. But there are extra layers of security when it comes to protecting your digital interests. The Nord Pass, the password manager, and the Nord Locker, which is a file encryption tool. So you can get all that in one easy package at a very low price with a 30-day money-back guarantee. You can try it risk-free. So log on to nordvpn.com/spacenuts. Use the code word spacenuts to get that deal with that extra 4 months free. That's nordvpn.com/spacenuts and use the code spacenuts. Now, back to the show.
3, 2, 1.
Space Nuts.
Now, Fred, we've been talking a lot about the James Webb Space Telescope and some of the fabulous images that it's been sending back to us, the latest being those incredible images of the aurorae on Jupiter. The way they did that was exceptional, and so many more things that we've seen already, and many more to come, assuming those micrometeoroids don't cause more and more trouble.
That's right.
But there's a new image in the news, which is the sharpest image ever of the star R136A1, which just so happens to be the biggest star in the universe. You've got to tell us how big this thing is.
Well, it's not as big as they thought it was. That's
that's
the original estimate, which comes from observations made with the Hubble Space Telescope, which has been kind of setting the yardstick for the amount of detail that you can see. The original estimate was between 250 and 320 times the mass of the Sun. But the new observations push that down. They suggest it's only 170 to 230 times the mass of the Sun. So it's gone from about 300 times the mass of the Sun to about 200 times the mass of the Sun on average. But that doesn't mean that its mass has changed. What it means is that we're seeing a much sharper view. And I think this is a staggering story, really, Andrew, because the space telescopes are the ones that can produce the most high-resolution images, the ones with the sharpest detail, because they don't have to contend with the Earth's atmosphere, which blurs the light, distorts it. But this particular observation that's given us a better view of this star and has allowed us to distinguish it from other nearby stars, which is why it's you're actually able to push down our estimate of its mass, because it's not mingled with other stars in the image that you're seeing. That image has come from a ground-based telescope, a very good one. It's one of the two Gemini telescopes, or Gemini as they tend to call it here in Australia. The Gemini telescopes, there are two of them, one in Hawaii and one in northern Chile. And they're identical. They have mirrors I think it's 8.1 meters in diameter. They're certainly more than 8 meters. I think they're 8.1. And they are equipped with some very fine instrumentation, including an instrument which on the Hawaiian telescope is called Zorro.
Oh, very good.
And because that means sorry, did I say the Hawaiian?
No, I think
I meant the
Chilean one.
I meant the Chilean. Yes, I beg your pardon.
Makes more sense.
But it does make more sense, yes. Zorro being the Spanish word for fox. It's on the Chilean telescope. The twin instrument in Hawaii is, as you can guess, this is a much more Hawaiian name, Alopeke, with a glottal stop on the A, a bit like Oumuamua. You've got to start with a glottal stop, Alopeke. That's the word for fox in native Hawaiian language.
Uh-huh.
So Zorro in Chile, Alopeke in Hawaii. But they're on identical telescopes, and effectively they are identical images. And what they're doing is a trick that sort of came to prominence, I guess, 20 years ago, something we call Speckle Interferometry. And it relies on the fact that when you look at the blurred image formed by a big telescope, when it's looking through the Earth's atmosphere, you might think that you've just got a blurred mess, and indeed that's a bit what it's like. It just looks like this blurred. In fact, I can tell you, it looks a lot like a football kind of wobbling in space, the image of a star, when you see it through the atmosphere. Of course, I saw that many, many, many times on the Anglo-Australian telescope, so on a TV screen, of course. Anyway, it turns out that if you can take really rapid snapshots, 1,000th of a second or something like that, of that blurred blob, it's not just a featureless blob. It's got what are called speckles in it. Oh. It breaks up into speckles, which are tiny individual images of the star that you're looking at. And that's because what the atmosphere does is as the turbulence in the atmosphere passes in front of the telescope, there's a kind of characteristic cell size in the turbulent blobs. So you've got a little warm blob that's got a slightly lower refractive index and a cold blob next to it with a slightly higher refractive index. And these have a characteristic size, which is usually and it's the size that actually determines. It's called the R. I can't remember what R stands for, but it's R is what we call it. It's measured in meters. The bigger the R value, the less turbulence there is. So small R values are very turbulent, big R values aren't. And typically a meter would be really good, a good measure of turbulence. But you can imagine that if you've got all these small blobs passing over the sort of window that the telescope's looking through, in other words, across the mirror of the telescope, each one of those blobs is going to produce its own image of whatever it is you're looking at. And that's how these speckles arise. They're sort of sub-images formed by the individual, the individual blobs of warmer or cooler material in the atmosphere, the characteristic size of these little turbulent cells, as they're called. And so if you're quick, and as I said, 1,000th of a second exposure, you can, and if you then take a video of these things, each with 1,000 seconds, you can sort of map the way these speckles move in the image plane, and you can actually then reconstruct what it is you're looking at with such fine detail that you're essentially only limited by the laws of physics. It's what we call the diffraction limit of the telescope. Big telescopes can see finer detail than smaller ones. That's just the way physics works. And in fact, this telescope is considerably bigger than the Hubble Space Telescope, which has a 2.4 meter diameter mirror. This is 8.1. So its speckles are smaller than the Hubble's would be if the Hubble was on the ground. But what it means is that you can resolve finer detail. And actually, I might recommend that listeners and viewers go to the NOIRLab site, NOIRLAB, which is the National Science Foundation's. It's actually the National Optical Infrared Laboratory. It stands for. It used to be called NOIR, but it's now. No, what was it called? NOAO. That's right, National Optical Astronomy Observatories. It was NOAO. It's now NOIRLab. They've put out a press release, which is headed "Sharpest Image Ever of Universe's Most Massive Known Star," and on that website you'll find a really compelling side-by-side view of this region of space. It's actually in the Large Magellanic Cloud, 160,000 light years away, centered on R136A1, which you've already told us. And you can see the image formed by the Zorro instrument on the Gemini South telescope and the image formed by the Hubble Space Telescope. And I have to say, the Hubble comes off second best in that comparison.
Doesn't it?
It's quite extraordinary. Yeah, we're used to Hubble setting the yardstick, but not this time.
Well, we've replaced it now, so...
Yes, sadly, this instrument will outperform the James Webb Space Telescope as well. But of course, the two, this is only very, very specialized observation. It's not looking at particularly faint objects. These are objects that will be, visible in a smaller telescope, 17th magnitude. It's not particularly.
I know somebody's wondering, but being the biggest known star in the universe, what kind of star is it?
It's a big star, so technically known as. It's the biggest stars and the hottest are what we call OB stars. That's their spectrum classification.
Did you say obese stars?
Not obese, but they are. O and B. So remember, spectral. The early astronomers classified the spectra, the rainbow spectra of stars, and started off calling them A, B, C, D, E, F, G, but it was soon realised that didn't mean much. In fact, if you order them in temperature, it goes O, B, A, F, G, K, M. And I don't know whether you remember the mnemonic for that. Oh, be a fine girl or gal or guy, kiss me.
Right.
Sometimes there was an R and N on the end. Right now was the answer for that. So O stars are the hottest, very, very hot, very massive stars.
So that's what it is.
Very likely.
Yeah. And are they common?
No, they're rare. They're very rare. And that's why this is such an important observation. And especially, when it's the record holder, when it's the one that we think is the most massive star ever observed, it still is, even with that reduced waistline that we've just given it, in pushing it down to 200 times the mass of the sun. It's still the most massive star observed.
That's because it's found the internet and got itself a diet coach. But I reckon.
Is that what you do? Yeah.
It's got its own Instagram account and
a stellar diet coach. Yeah.
Maybe so.
Good. Trouble is, that was all the light that we're getting from that is 160,000 years old. They might have had the internet in the Large Magellanic Cloud 160,000 years ago.
Are those kinds of stars, O stars, long-lived?
No. Thank you. You're asking all the right questions, Andrew. They're not, actually. They don't last for very long. A lifetime typically 10, 20 million years compared with the 10 billion years that is our sun's lifespan. Wow. And in case you're wondering where this star came from, it's right in the heart of what's called the Tarantula Nebula in the Large Magellanic Cloud, which is a region where stars are forming. So it's it's a star-forming region, and this is one that formed maybe 10 million years ago, something like that.
So what would make it so big when other stars aren't? What factors go into that formula?
Actually, the fact that it's in the middle of a cluster maybe helps because if you've got stars all around you, if you think of the way stars form, they form in clouds of gas and dust, which basically collapse, not in their entirety, but what you get is sort of cells of material within those clouds that collapse into their own gravitational pulls them together, and they eventually collapse into stars. So if you've got a very dense gas and dust cloud, which is forming stars within its cells, and we've seen pictures of that sort of thing already from the James Webb Space Telescope, then the denser the material, the more likely you are to form massive stars.
So it just happened to be
forming a cluster.
The right circumstances with the right amount of raw materials, and wham, bam, thank you, ma'am, an obese star.
Yes.
Yeah. It's if you would like to see those images, the website that Fred mentioned is noirlab, noirlab.edu. Should not be difficult for you to find. Some great images there, and the comparison that Fred mentioned between Zorro and Hubble is staggering. It is quite amazing. Yeah. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
It is time to deal with some audience questions, Fred. We're going to try and squeeze 3 in today. 2 of them are text questions. The first one comes from Pablo. Hello, my name is Pablo. What a coincidence, because that's what I thought his name was. From Toronto, Canada. I've read about things called Dyson spheres. To my understanding, it is a ring that is around the star that acts like a gigantic solar panel. To my knowledge, they are still theoretical devices. So hopefully you can answer my questions. My question has 2 parts. 1, would this ring create a shadow on Earth or other planets, similar to how a tree creates a shadow for grass or on the ground? 2, if the purpose of this device is to harness a star's energy and convert it to electricity, how would you connect the device to the Earth? It would be difficult to have a wire running for 1 AU. Thanks, Pablo. I love this question because I actually read the answer to this question when I was looking at another story about how to harness the solar power of the sun and use it on Earth. But let's sort of deal with the 2 parts. Firstly, please explain a Dyson sphere.
Yeah, well, I hope the answer I give is the same one that you read, Andrew. So it goes back several decades, but a scientist whose name I should remember, but I'm afraid I can't. I did write about him because it was a him in Space Warp, and I should have grabbed Space Warp and had a look, but I'm not going to do that. I'm just going to waffle. This particular scientist classified potential civilizations, and we're talking now about extraterrestrial civilizations, by their energy consumption. So, the lowest level of energy and the lowest level of civilization are those species that consume fossil fuels. Oh. So we're at the really dim end of all this. And then you've got several stages collecting all the radiation that falls on a planet, if you can do that, and utilizing that. But the highest level is of extraterrestrial civilization, which demands the most energy. The speculation is that you collect all the energy from your star. And it was another scientist whose name was Dyson who said, well, that's the way to become the most energy efficient that you possibly could be. You build a mega structure around the star, which will collect all the energy that the star emits. So this is not a ring, it's actually a sphere that you build around the star. It collects all the radiation, and then, yes, you've got your wire, 1 astronomical unit long. I think what you have to imagine is that the utilizers of this radiation are so advanced technologically that they just flit around in space. They don't really need a planet. And they collect the radiation wherever they can find it. That might be a bit flippant, but the idea is that the solar panels are collecting all the radiation. I suspect you'd live on the megastructure, actually. You'd find some way to live on it rather than worrying about being on a puny planet.
Yeah, probably the outside would make sense.
Yeah, although I've wondered about that. Do you put it on do you put the Dyson sphere outside the Earth or inside outside the orbit of the Earth or inside the orbit of the Earth. And I think you're right. You've got to put it on the inside because otherwise there's going to be quite a lot of thermal radiation coming from the thing inside. There is outside as well, actually. The Dyson sphere will emit infrared radiation because it will get warm. And that's how people have been looking for them, just to cut to a question that wasn't asked. Some astronomers have been looking for a kind of infrared signature that would come from a megastructure around a parent star that was collecting all its radiation for an advanced civilization, but getting warm in the process and radiating infrared on certain wavelengths. They haven't found anything so far. They haven't found anything, which is why we don't think these things exist. But it's a figment of the imagination. So would it cast shadows? Well, yes, it would. If it's a sphere around the whole star, it's going to block out all the light from the star, and all you'll see will be indirect radiation from the Dyson sphere itself.
Yeah, it would have a massive impact on the Earth's ecology, I imagine.
Yes, I think that's right.
So, yes, there would be shadows. Now, as for how you'd get the energy to Earth, I read a story, I think it was yesterday, about the idea of putting satellites into space and harnessing the energy of the sun and beaming it back to solar panel fields via laser.
Yeah, that's right. It's reared its ugly head again as this, because 30 years ago there was work done on doing what you're just talking about, but doing it. Sorry, I'm just kicking the window because there's the rogue cat has come into our yard, and our cat doesn't like him. So if I kick the window, it scares him away. There we go. He's gone. Sorry, this is cat wars here. Sorry about that. So the idea was raised many years ago of doing that, putting solar panels in space and beaming the energy, the electricity, down via microwaves. So you beam microwaves, which are what's inside your oven, down onto the Earth's surface.
Yeah.
And that always seemed to me to be a bit dodgy as an idea. But now it's moved into a different regime because we're now talking about laser communications in space and things like that. So people are talking about beaming the energy down with lasers.
So that could be the answer, Pablo. And it's starting to become affordable. That's what's interesting about that story. It is actually starting to look like it could be feasible at the very least. So there might be some news on that in the future. Thanks for your question, Pablo. We'll go to another text question. Hey, guys, great show. Is he talking about us? David here from Dallas, Texas. I had a question about the barycenter between the Earth and the Moon. Since the Moon is moving away from the Earth slowly, at what point will the barycenter move outside the Earth's interior? And then what will we call the Moon?
It's a brilliant question.
It is a lovely question.
But it gave me a sleepless night, Andrew, because that came in. It came in late on Friday evening. I don't know whether you remember. We got it from Hugh.
Yep.
And I read it just before I went to sleep. And so I did the calculation the whole night. It was, it was one of those things. You're half awake, you're half dreaming, but this damn thing about the barycenter kept cropping up the whole night. Yeah. But by the morning, I'd worked it out, and I actually got it wrong because I forgot to add a 1 in the formula, but that's all right. It didn't make that much difference. So let's just unpick the question. If you've got two objects orbiting one another and they're of similar masses, then they will orbit around the barycenter, which is their common center of gravity. Yeah. If you've got a large object and a small object, the barycenter moves towards the larger object. And if you've got a large object and a very small object, the barycenter is inside the larger object. And that's the case with the Earth and the Moon. So the Earth-Moon barycenter it's actually not as near the middle of the Earth as you'd think. It's 75% of the way up to the surface of the Earth.
Oh,
It's actually, quite high. And of course it moves. It twists around. It's an imaginary point, but it moves as the moon goes around the Earth. So the calculation that kept me awake was how far away does the moon have to be for the barycenter to emerge from the surface of the Earth?
yeah.
And I'll tell you the answer. Well, the moon is 384,000 kilometers away now, 240,000 miles. Is that right? From my old days when I used to work in miles. Anyway, 384,000 kilometers. It would need to be 514,000 kilometers, more than 500,000 kilometers away. At that distance, the barycenter is on the surface of the Earth. And so it will... any further, and the barycenter is between the Earth and the Moon. However, I also worked out that if the Moon keeps going at the rate it's going at the moment, which is 3.82 centimeters a year, and it keeps on going at that speed as it leaves the Earth, it will take just over 4 billion years for the Moon to get to that point where the barycenter pops up from the Earth's surface. But that's never going to happen because long before that, the Moon's motion will have stopped. Actually, in fact, maybe not long before it. We think it's still a few billion years, but perhaps I can qualify this a little bit. What will happen is that the Moon's motion away from the Earth will slow down gradually. Yeah. So the calculation I did that gave me 4 billion years was if it keeps going at 3.82 centimeters a year, but it's not going to do that. It will slow down because as the Moon draws energy from the Earth's rotation slows down. And remember, they're going to wind up with this equilibrium situation where the Moon and the Earth always face one another. The month and the day will be the same length, which is 47 of our present days, and the distance between the two will be about 500,000 kilometers. So that means the barycenter will never come out of the body of the Earth. It will always be lurking somewhere beneath the surface when we get to that equilibrium situation.
Let's say it did. Would people on the surface that are in that barycenter feel anything?
No, they wouldn't. There wouldn't be. There would be tidal effects, a bit like what we've got now. They'd be a bit more complicated, but it's a really interesting thought, isn't it? Oh, the barycenter's here, but it won't be here for very long because as the Moon goes around the Earth, it's drifting with it. The Earth's moving as well. But the last bit of David's question: if physics was defied and the barycenter did emerge from the body of the Earth, what do you call the Moon? Well, that's a good question because it stops being a satellite of the Earth and it becomes a companion double planet. The Earth Moon becomes...
It's too small to be a planet, isn't it?
It's too small to be a planet, so it's a planet and a dwarf planet, but it's a double planet. So the Moon becomes a dwarf planet.
But it would have to retain its name Luna, wouldn't it?
Yeah, that would never change that.
See,
that's in with the woodwork.
Pluto is still Pluto, even though it got deregistered as a planet.
That's right. Pluto's a good example, though, because Pluto and Charon are, the barycenter is in between them because Charon's half the diameter of Pluto. It's much bigger. I should have said the Moon is only 1/80th of the mass of the Earth, and that was the number that I had in my head when I was doing this calculation in my sleep.
Very good. All right. There you have it, David, a pretty detailed explanation of the whys and wherefores of the barycenter. Now, we're going to throw to another question. This one's an audio question from Buddy in Oregon.
Hi, guys. It's Buddy again from Oregon. Hey, when you're talking about the microwave background radiation, when you said that it's microwaves because it's been stretched until it's only now just a microwave, is the light been stretched or is the space been stretched?
Thanks, Buddy. Thanks for your support. Buddy sent us a lot of questions, so I just thought I'd throw that one in because it's a good question. What's been stretched in the process of the microwave background radiation, which is the remnant of the Big Bang?
So yes, it's and the answer is both, in fact. So what we've got here is a scenario where we're looking so far out into space that we eventually, because it's always looking back in time as well, we eventually look back to a time when the universe was not transparent. So light didn't go through it. It was a blinding fog of radiation. So what you're going to see when you look back so far, what you're going to see is a radiation all the way around the sky. And if the universe wasn't expanding, our sky will be brighter than the sun.
Oh, wow.
Everywhere. But because we'd be looking back to a time when it was, still shining brightly. But of course, since that radiation was emitted, the universe has expanded by, I think it's about 1,300 times the factor by which it's expanded. And what that does is it changes visible light by stretching the light. So it's the light that's being stretched by the stretching of the universe, and it turns into microwaves. So the waves themselves have been stretched as they pass through the universe.
Okay, there you are, buddy. Great question, and it's probably not one that many people think of, to be honest. But great to hear from you. A question without notice, Fred, very quickly. One of our regular YouTube viewers, because we go out live when we're recording and we package it up later to make it actually sound good for the for the internet. One of our regular YouTube viewers is wondering if there's any news on the Magellan Telescope.
Yes, there is actually, and that's a great prompt. The Giant Magellan Telescope, which is the sort of 23-meter equivalent, it will have 7 8.4 meter diameter mirrors, which are arranged in a kind of flower petal pattern, being built at a place called Las Campanas, which means the bells, and that's because the rocks actually ping like bells if you ping them. I've been there and seen it. There's a big hole in the ground, which is where the Giant Magellan Telescope is going to go. So it's in northern Chile. It's a venture, multinational venture. We in Australia have a small role in it because we contributed to the kickoff funding, and we're also designing and building an instrument for it. But the reason why it's been in the news is that last week, I think it was, the National Science Foundation in the US allocated an extra tranche of funding to it of $205 million US, which is really, really good news, because the problem with big telescopes is they always cost more than you thought they would, and the money you started off with at the beginning is not going to last, and so that's kind of what's happening. I might just throw in, as well as that good news, I was at a colloquium, a seminar a couple of weeks ago, given by one of the Giant Magellan Telescope team, and it was about the cell that will hold each of these 7 giant mirrors. They're huge, 8.4 meters in diameter. So each one has to have a mirror cell, which is the apparatus that supports a mirror so that it doesn't flex and bend. And they're building a test one. In fact, they've built it and they're doing tests on it just to make sure that this is going to work before they build 6 more to make up the telescope, because these things are all arranged on a central axis. It's going to be a marvelous structure when it's built, but the detail that these scientists and engineers are going into, and the amount that they've achieved so far, it was really staggering. It was a very, very impressive talk.
Fantastic. All right. And we've just received a big thank you from the person who asked that question. So, glad we could help you out. And I've got another one without notice, Fred. This comes from one of our Facebook followers, and I know this bloke, Paul Keane, because we often swap messages on Facebook. And we would have had to do this next week because someone would have asked anyway. But if it was 100,000 years later, we're talking about the second asteroid to just that hit off Africa that we talked about earlier. If it was 100,000 years later, would there be an identifiable ring of iridium separate from the one left by the Chicxulub hit?
Maybe. So the iridium was the clue for that dinosaur extinction was caused by something from space, because iridium is found in space objects. There might be. That would put a different an additional layer of iridium. Now, 100,000 years geologically might not be that long to separate these strata as they're laid down. But yeah, I'm sure people will be looking for that. It's a great thought.
It is indeed. Good on you, Paul. Lovely to hear from you, and I'll see you on Facebook. Now, that just about wraps it up. Fred, of course, if people do have questions, and we got a whole raft of them after last week's desperate appeal, we'll try and get through those. And but if you do have questions, go to the Space Nuts website, spacenutspodcast.com or spacenuts.io, and you can ask your question through the AMA tab or the Send Us Your Audio Question or voice question on the front page. And I do have a little bit of news to share with you. We are going to be trialling a brand new podcast. In fact, the first edition has been recorded and probably will be out any time now. It's going to be called Astronomy Daily, and it's going to be, well, ultimately a daily podcast, 10 or 15 minutes, just going through the news of the day from Astronomy Daily. On what's happening in astronomy and space science. So I hope you'll join me for that one. Fred will be an occasional guest. He can't commit to a daily thing. We did ask him, and he just gave me a flat-out no. But
that's because I've got a job.
Yeah, I've got about 7 of them now. But yes, keep an eye out for it. Astronomy Daily. I will have a co-host. I won't reveal anything, but it's something quite different. And the fact that I've called her Thing probably gives you a bit of an idea. But anyway, look out for it. Astronomy Daily, the trial episode or pilot. We called it pilot, won't we? Yeah. The pilot episode is out very, very soon. Well, by the time this is out as a podcast, it will be out anyway. So look for it and let us know what you think. It's a work in progress, but really looking forward to Astronomy Daily. I don't know where I'm going to fit that into my repertoire. Got too much to do, but it'll be a lot of fun. Thank you, Fred. As always, it's been a great pleasure.
And thanks, Andrew. Next week, hopefully, we might have news on the Artemis 1 mission.
I was about to wish them well. Artemis is due for liftoff around 8:30 Eastern Daylight Time in the United States and on the 29th of August. All things being equal, and you can watch it live on NASA TV, by the way. So, that will be really exciting. So, yes, fingers crossed we'll have some good news regarding Artemis 1 next week because my name's on it. I've got a boarding pass.
Yeah, I know. Your boarding pass is on it.
Yes, so that'll be fun. All right. Thanks, Fred. We'll see you next week.
Sounds great. Thanks, Andrew.
Fred Watson, astronomer at large, part of the team here at Space Nuts. And, of course, thanks as always to Fred. Always say thank you to Fred, but thanks to Hugh in the studio who's pushing buttons and picking his teeth and all sorts of other exciting things. From me, Andrew Dunkley, thanks for your company. We'll look forward to joining you next week on another episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.